So in this video, we want to review problem 2.105 from the chapter 2 homework. If you notice here, we have a pole, which in the geometry that they've set up for us goes from the origin out to point A, and there is a force that's being exerted on the tip of that pole. And again, it's a force that is associated with the pulling of a cable. So you actually call that a tensile force. We're given an expression in Cartesian form for the force that's acting upon the cable at A. And what we're asked to do is to find the projection of that force onto the axis defined by the pole. So if you think back to the chapter 2 material that we did a little bit earlier, whenever you want to project a vector onto an axis, there's a lot of different ways to do it. You can actually draw the geometry and involve the cosine of theta and all these things. But the easiest way to do it is always if you have an expression for a unit vector along the axis on which you're trying to project. So really this just boils down to, since you have an expression for f in Cartesian form, if you had a unit vector along the axis defined by that pole from A to the origin, you could just take a dot product with that unit vector and the actual problem would be done. So the question is, how do I go about writing a unit vector from A to the origin? Well, fortunately, if you notice, I'm given enough geometrical information that I can find the coordinates of both A, and naturally I know the coordinates of the origin are just X, Y, and Z. Coordinates are all 0. So how do I get to point A? And I know my drawing is very bad, I'm sorry. But if you notice, you move out along the positive x-axis. We know it's positive since we note that the coordinate system they've given us has the actual arrow on this end of x. So we're moving out in positive x by 3 feet. Then we're moving actually in negative y, since positive y, the way that I have this drawn, goes to the right. We're moving in the opposite direction. It would be negative 2. And then from there, we're moving up, right, in the direction of positive z by 6 units. So the first thing we need to do is write an expression for that coordinate of A, and that's exactly what I've done here. Just again to check, positive 3 for x, negative 2 for y, positive 6 for z, and that's what we have. And of course, the coordinate of the origin is just 0, 0, 0. So if I want to write a position vector that goes from A to the origin, and this is something that we're going to do quite heavily again in the next video. Actually, I just talked about that if you look at my clock, so doing these in reverse. But when you write a position vector from one point to the other, you just kind of envision, okay, what's my tail? My tail's up here at A. My tip's at the origin, so like the actual head of the arrow is going to be down here on the origin. And whenever I'm trying to write a position vector, I take the points of my tip and the points of my tail, and I subtract them on a per coordinate basis. And I take those difference and I weight them by the unit vectors. So one of the nice things in this case, since the actual tip of that vector is at the origin, really all that's going to happen is you're taking the coordinates of A, and you can kind of see it here, and you're just flipping the sign. So the position vector, if you're writing a position vector from point A to the origin, and the coordinates of A are 3, -2, and 6, the position vector is just going to have all of those signs swapped. It's just going to have an x component of -3, a y component of 2, and -6. And the reason you can kind of see that is just ask yourself, if you were at point A and you had to walk to the origin, what direction do you have to walk in x? Well, you have to go back in along that x-axis. So your x displacement to go from A to the origin is actually going to be negative. So it's not surprising that turns out to be a negative value. So in general, whenever I write a position vector, because it's so easy to make these mistakes subtracting with signed numbers, I always go back and just check, okay, to go from A to the origin, do I have to go, since the x component is negative, do I have to go back in x? Yeah. Am I moving in the positive y direction? Well, yeah, according to the axes that we have set up, that's true. Am I moving in negative z? Well, yeah, I'm going, remember z is measuring elevation in this case, and I'm going from a high elevation to a low elevation. So this is a reasonable position vector according to the geometry that I'm given. Whenever I want to write a unit vector, if I have any vector, I just take it and I divide by its magnitude. If you think about it, the magnitude of that original vector you're working with, whatever it is, when you divide by the magnitude, as we discussed in the lecture part of the chapter 2, that will just have the magnitude of 1. So how do you find a magnitude of this position vector? Well, just take the square root of the sum of each component squared. Whether the components are positive or negative, when you square them, they will turn out to be positive. Do that math, and what you will find is that position vector has a length of 7 feet, which means that the actual physical distance from point A to the origin is 7 feet. So if I were to take that and scale and create my unit vector, I get this quantity that I have written here. So there are two things that you could verify if you want. You could take the magnitude of this, and you better get 1. In addition, note that this won't have any units because the position vector was in whatever distance units this problem was given in this case, feet. Its magnitude is clearly in feet. So when you divide feet by feet, you get something that's unitless. And that's what allows the unit vector to actually serve as kind of our key source of direction information. And we're going to talk about that in the next problem where we're going to take a magnitude of a force, multiply by a unit vector. Remember, as a scalar times a vector, so we're just scaling each individual component. And we're going to claim that, hey, that resulting thing that now is in Cartesian form, it has the same units as the original thing. And the reason that it does is that the unit vector is actually unitless. So how do I, once I have a unit vector along a particular axis, in this case, an axis going from point A to the origin, how do I find the projection of a vector onto that axis? Well, all I have to do is take a dot product. So if you notice, this notation just says that to project F onto the axis AO, take the vector F and take a dot product with a unit vector from point A to point O. Here's the unit vector that I computed above. Here's the force that I was actually given. And if you do everything correctly mathematically there, you should find that your final answer is 50 pounds. So hopefully that was helpful to you, and I will see you in the next video.